Alright, now we're going to look at polar molecules. So again, this is all based on electronegativity, and we need to be able to evaluate polar bonds. So you remember, a polar bond, or a bond, exists between two atoms. So if we look at NH3 here, NH3 has three different bonds, or actually three bonds that are the same between nitrogen and hydrogen. Carbon dioxide has two bonds, in this case two bonds that are the same between carbon and oxygen. So we have to evaluate those bonds to see if there is polarity, if there is an unequal sharing of electrons. And again, that is based on our electronegativity reference. So I'm going to kind of start off the same way we did when evaluating polar bonds. I want to determine if NH3 has polar bonds. So I'm going to look at nitrogen, which has a value of 3.0, and hydrogen, which has a value of 2.1. That's an electronegativity difference of 0.9. So yes, it has polar bonds, but it doesn't necessarily mean that it's a polar molecule. In order to determine if it's a polar molecule, we have to look at its molecular geometry. We have to look at the shape of the molecule in order to determine if there is a partially positive side and a partially negative side. That's what defines a polar molecule. So it's kind of the same idea as a polar bond. In a polar bond, we're going to have one side of the bond is slightly negative, and one side of the bond, and the other side of the bond is slightly positive. Same idea, but now applied to the concept of a molecule. So if I look at this, nitrogen, which is my pink atom here, has greater electronegativity. Electronegativity of 3. So it's going to pull the electrons closer towards itself, making this side of the molecule more negative. And this is a three-dimensional model, so it can be difficult to see. Then the white side would all be positive. And you can't really see it here, but if you could picture that three-dimensional model, there would be the pink side and the white side. Picture a pyramid, right? This is a trigonal pyramidal shape. So in this case, the top of the pyramid would be pink, and it would be negatively charged. The base of the pyramid would be white, and it would be positively charged. That meets the definition of a polar molecule. One side being slightly negative, one side being slightly positive. So yes, this is a polar molecule. Now let's take a look at another example. We have carbon dioxide. Again, we're going to start off by determining if it has polar bonds. Carbon has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5. So its electronegativity difference is 1. So yes, it has polar bonds. Now we have to, again, look at the molecular geometry, look at its shape, to determine if it is a polar molecule. In this case, oxygen has greater electronegativity. That's going to pull the electrons in this direction, making this side slightly negative. But it's also going to pull those electrons in this direction, making this side slightly negative. Now in this case, the inside would be more positive. But if I look at the definition, I do not have one side that is slightly negative and the other side being slightly positive. In this case, both ends of my molecule are negative. So this is not a polar molecule because it does not have one end that is positive and one end that is negative. In this case, that's because of its linear molecular geometry.